Alkanes are generally considered unreactive as they have no functional groups present. They only contain strong carbon-carbon or carbon-hydrogen sigma bonds, and since carbon and hydrogen have a very small difference in electronegativity, none of the bonds in alkanes is polarized. As a result, alkanes do not react with nucleophile or electrophiles. However, reactive species with unpaired electrons, which is the free radicals, will play an important role in the reactions of alkanes. The common reactions of alkanes can be summarized as combustion and halogenation. We will look at each of these reactions to begin understanding on how organic reactions proceed. Like all hydrocarbons, alkanes burn in plentiful oxygen or air to produce carbon dioxide and water. In a slightly limited oxygen supply, the combustion of alkenes will produce carbon monoxide and water, while in a very limited oxygen, alkenes burns to form carbon and water only. The combustion of alkane can be represented by the following equation. So for example, if we have a butane, okay, from its structural formula, the molecular formula of butane is C4H10. So, the combustion of alkane in excess oxygen will produce carbon dioxide and water as its products. So, balance the equation. Since we have 4 carbon on the left side, so we have to times the carbon dioxide with 4, right? And then the hydrogen is 10, so 5 times 2 equals to 10. And then balance the oxygen. So here we will need 13/2 oxygen gas. While if we burn our alkane in a slightly limited oxygen, it will produce carbon monoxide and water. So balance our equation. We will get 1 moles of butane reacted with 9/2 moles of oxygen produce 4 moles of carbon monoxide and 5 moles of water. Alkanes or cycloalkanes will react with halogen, which is chlorine or bromine, at elevated temperature or in the presence of light to produce an alkyl halide. The high temperature or light will supply energy required to break the chlorine or bromine bond homolytically into chlorine or bromine radicals. So, at room temperature, alkanes do not react when it is mixed with chlorine or bromine in the dark. The halogenation of alkenes is a free radical substitution reaction in which a hydrogen is removed from the alkane and a halogen takes its place. The halogen atom can substitute at any site on the molecule. The halogenated products actually it can react further to give a more substituted products. This reaction is therefore not at all selective and mixtures of many products will form. For example, the chloromethane may undergo further chlorination to dichloromethane and ultimately the products can also include trichloromethane and also tetrachloromethane. Since there are so many products produced, this reaction is not very useful in the laboratory, but it is useful in industry for the production of the various chloromethanes. So for the halogenation of alkenes, our focus is only for the mono substitution of alkenes. So it means that only one of the hydrogen from the alkenes is going to be substituted with one halogen. For alkenes that have equivalence or same type of hydrogen, when it undergoes bromination or chlorination, it will yield to only one alkyl halide product. For example, in ethane, these two carbons are symmetrical to each other. This is a primary carbon and all the hydrogen here is also a primary hydrogen, while this carbon also primary carbon and all the hydrogen here is the primary hydrogen. So since these two carbons are symmetrical to each other, if we replace one of the hydrogen here with bromine, it will give us a bromoethane. If we remove one of the hydrogen from this carbon, also it will give us bromoethane. For a non-equivalent type of hydrogen, for example, the propane, right? So we have three carbon in propane. The first carbon here is the primary carbon, while the second carbon here is the secondary carbon, and the third carbon here is also primary carbon. So all the hydrogen that attached to the primary carbon is a primary hydrogen, and the hydrogen that is attached on the secondary carbon is a secondary hydrogen. So since these two carbon are symmetrical to each other, so if we replace the halogen, okay, from this carbon, okay, we replace one of the hydrogen to halogen from this carbon, it will give us same product if we replace it from this carbon, because these two carbon are symmetrical to each other. Okay, so if we replace the hydrogen from this or this carbon, okay, we replace it with bromine, okay, it will give us one bromopropane. Okay, it still give us the same product because it is symmetrical to each other. But if we replace one of the hydrogen from the secondary carbon, it will give us 2-bromopropane, which is the other product. So the monosubstitution of alkanes can yield to a mixture of alkyl halide if there is more than one type of hydrogen present. The product formed in the free radical substitution reactions of alkanes depends not only on the number of hydrogens available for the extraction, but also on the relative strengths of their carbon-hydrogen bond. Hydrogen that is attached on the tertiary carbon will have the weakest CH bond. As we can see here, the more alkyl group attached to the CH bond, the weakest the CH bond. So, if the bond between the carbon and hydrogen is weaker, the more readily the hydrogen to be removed, so more stable radical will be formed, and it will lead to the formation of major product. So if we look at this reaction, since the bromination of propane will lead to two alkyl halide product, which is 1-bromopropane and 2-bromopropane, since the secondary carbon will give a weaker CH bond compared to the primary carbon, so 2-bromopropane is the major product of bromination of propane.